Hello, this is Malachi Bishop, and this is RC-750 Rehabilitation Counseling Research and Program Evaluation, and we are in our Week 5 discussion of inferential statistics, and in this section we will be talking about parametric and non-parametric data and statistical tests, and then we will be looking at some parametric statistical tests of difference. We'll get to what that means in a few minutes, but let's begin by discussing the idea of parametric and non-parametric data and tests. First of all, the idea here is finding the best statistical test for the data that you have collected, and parametric data are data that are measured using interval or ratio level scales and are normally distributed. And then non-parametric data are data that are recording using nominal or ordinal scales, and these are not normally distributed. So based on the sort of data that you have collected, you can do either parametric or non-parametric statistical tests. So parametric tests, let's talk about some of the characteristics of parametric tests. First of all, parametric tests have strict assumptions about the data being analyzed. Specifically, at least one variable must be measured at the interval or ratio level of measurement, and the interval or ratio variable must be normally distributed. So the data must be normally distributed and measured on an interval or ratio scale. And if you are comparing different groups, two or more different groups, then the members should be randomly assigned to meet the test of independence. So remember, we talked about independence, meaning that each member has an equal opportunity of being selected for either group, and the members are independent of each other. Parametric tests are more sensitive and more precise than non-parametric tests, and this is because, as we said, parametric tests deal with data measured using an interval or ratio scale, and so those interval and ratio scales provide more precise data than data that are measured using rank ordering or ordinal or nominal data. Parametric tests include, for example, the t-test and the analysis of variance, or ANOVA, and the Pearson product moment correlation. And we'll be looking at each of these. Non-parametric tests do not require these assumptions about the data to be met. They can be used to analyze relationships between nominal and rank order or ordinal data, and they are particularly useful when the sample size is small. The non-parametric tests include things like the Mann-Whitney-Wilcoxon test, the Wilcoxon-Sign-Ranks test, the Kruskal-Wallis test, and the chi-square. Among these, we will be talking about the most frequently seen in the rehabilitation counseling literature, the chi-square. So we'll be looking at that statistical test a little later on. Basically, for every parametric test, there is a non-parametric counterpart. So when you have a large number of people in your sample and you have data measured on an interval or ratio scale, then the parametric tests are more precise and sensitive. But when you find that your sample is small, or all the data are measured using nominal or ordinal scales and are not normally distributed, then you will end up using a non-parametric test. So basically, the data that you have determines the test that you do. So now we will get into looking at a couple of the most frequently used parametric tests. And parametric tests may be distinguished in terms of tests of difference and tests of relationship. So you can be doing an analysis to identify that whether or not there are differences between two or more groups, or you can be looking at the extent to which variables are related to each other. And so we're talking about different kinds of tests for tests of difference and tests of relationship. We're going to begin with looking at tests of difference, including the t-test and the analysis of variance. And then later on, we'll look at parametric tests of relationship, including the Pearson product moment correlation and regression analyses. In terms of tests of difference, the t-test and analysis of variance are parametric tests that are used when the researcher wants to explore differences between groups. There are two different tests because they have different capability. We use the t-test when we have just two groups and we want to compare the means of the two groups and see if there is a statistically significant difference between them. Analysis of variance is what we use when we want to explore whether differences between the means of two or more groups. So if we have 3 or 4 or 5 groups and we want to see if there are differences between the groups, then we would have to use the analysis of variance. And we'll look at the reason for that after we get into how these tests work a little bit. So for example, if you were doing a test like with two groups and you wanted to compare whether the means of the two groups were statistically significantly different, then you could use a t-test. But if you throw in a third group, like for example, if you wanted to find out whether medication or talk therapy or some combination of talk therapy and medication was most effective on alleviating depression, you would have to use analysis of variance. So we will begin by looking at the t-test, which answers the question, how do two group means differ on some variable of interest? And the t-test compares the means of two groups, taking into account 3 elements. So there are 3 elements involved in the calculation of the t-test: the mean, the sample size, and the variance. We use this test when we want to know if there's a difference in the average or mean score between two groups, and the t-test tests the null hypothesis that there is no difference between the sample means, or that the sample means are equal. So as we've talked about, you begin your calculation of a parametric test with the statement of the null hypothesis. So we'll look at that in a minute. The t-test is used to assess the significance of group differences, and as I said in the last slide there, 3 things are considered: the magnitude or size of the mean difference between the two groups, the variance of the groups or degree of overlap in the scores, and the spread of the scores. Remember, variance refers to how spread out the scores are. And then the third component of calculating the t-test is the number of participants in your sample. So let's walk through the process of conducting the t-test. As I said, the first step is to establish your hypotheses, the null and the alternative hypotheses. And we've talked about the null hypothesis and said that essentially the null hypothesis is a testable statement of no difference, right? So the null hypothesis, when you're comparing two groups, is that the difference between the two groups, the mean of the two groups, is 0. There is no difference. So for example, the difference between the mean of the treatment group and the mean of the control group is 0. That would be our null hypothesis. The alternative hypothesis would be that there is a difference between the means of the two groups, and you can have a non-directional hypothesis or a directional hypothesis. A non-directional hypothesis would be the one I just said, that there is a difference between the means of the two groups, but we're not saying which group is going to be higher than the other. We're just saying that there is a statistically significant difference between the two groups. The directional hypothesis would be making a statement about one group being higher than the other. So we would say that, for example, if we had a group of males and a group of females, the directional hypothesis would say that the scores of the females will be higher than the scores of the male. The second step is to calculate the test statistic. And as we said, this involves 3 components, and we're going to look now at why it is important that each of these 3 components are included in the calculation. The first is the magnitude or size of the difference between the 2 groups. And here the issue is that the larger the difference is between each group's mean score, the more likely it is that the difference is due to experimental conditions rather than chance or sampling error. So if we have comparing these 2 means here in blue, and we see that they are different, they are one is about 5.5 and one is about 6.5. So the mean of this group is about 5.5, and the mean of a second group about 6.5. We can see that the 2 means are different, but we can also see that they're quite close together, and so we wouldn't be sure whether the difference between these 2 groups was really due to which group they belong to, or just chance or sampling error. Now, as we look at the 2 means represented by the yellow lines, where we see much larger magnitude in the difference, we have about a mean of 4 and a mean of 10, we can see that there is a much larger difference in the mean of the 2 groups, and we'd be more likely to conclude that this group, they were different from this group based on their whatever characteristic it is that we place them into the group based on. So again, if we're thinking about males and females, or experimental and treatment group, control and treatment group, if this was the treatment group and they were scoring means of around 10, and the control group was scoring means of around 4, we would, just looking at that, we would be more likely to think that there is a meaningful difference based on our treatment. The second component is the variance or standard deviation of both averages. The variance or spread of the data in each group is important in determining the distinction between the groups, because if there is a lot of overlap in the variance, then one is less confident in saying that one group is really different than the other. So for example, if we look at these diagrams here, based on the different distributions of the scores shown below, based on the distributions, the variance, the spread of the data represented in these 2 different pictures. The bottom picture down here shows scores with a smaller standard deviation. So the smaller the standard deviation, the less spread out the scores are. The larger the standard deviation, the more spread out the scores are. So this picture on the top shows a distribution to groups with a larger standard deviation, larger variance, larger spread of the data. And when you have overlap, like you do in the picture on the top there, it's less likely that there's a meaningful difference between the 2 groups. So for example, the top picture, where you have a lot of spread between the in both groups, this picture could represent the height of 4-year-old boys in one group and 4-year-old girls in the other. And you would see, and you'd probably expect to see, not much difference between the 2 groups. And so there would be a lot of overlap in the variance there. So hard to distinguish that there are actually 2 different groups there. Now, if the bottom one represented the height of 4-year-olds and 10-year-olds, then you would be more likely to see something like that, where there is less overlap, right? And it's clearly 2 distinct groups. In other words, you'd be more likely to think that the difference in scores was based on membership in the 2 groups and not on chance or sampling error. Then finally, the third component in calculating the t-test is the sample size. And this one is, if you think about this, if you have a sample of 4-year-olds, 2 girls and 2 boys, and you find that the girls are much taller than the boys, how confident can you be that the difference is based on a real difference in the population? you really couldn't be too confident based on a sample of 4 4-year-olds. But if you have 2 samples of 10 4-year-olds, and you find a large difference between them, where the girls are much taller than the boys, then you probably still not a tremendous amount of confidence that your finding represents a true difference in the population, but maybe a little more confidence. Now, if you have 2 samples of 400, so you have 800 4-year-olds, 400 girls and 400 boys, and you still find that the girls are much taller than the boys, and there's a significant difference between them, now you are increasingly confident that there is a difference in the population, and that your sample is identifying a meaningful difference that you would also find in the population. So the larger the sample size, the more confident you can be that the differences that you're finding are real. So that component is important too. So as I said, each of the t-test statistics calculate the t-test including those 3 components. There are different forms of t-tests, and different formulas are used to calculate the t-statistic. We will look in a minute at the different forms of t-tests, but let me show you an example of one of the formulas. This is the formula for calculating independent t-test formula. So if you're doing an independent t-test, this is the formula that you would use, and you can see you have the various components that I mentioned are all part of this calculation. You have the mean of the treatment group and the mean of the control group on the top there, divided by the square root of the variance of the treatment group, divided by the number of people in the treatment group. So you've got the mean, you've got the variance or standard deviation, and you've got the sample size. And down here you also have the variance and the sample size of the control group. So all those 3 elements that we talked about, the mean, the variance or spread, and the number of people in your sample, are all represented. So then you evaluate the significance of the results that you found. The t-test is a calculation of the size of the difference between the 2 groups, but we don't know, based on the t that we calculate, we don't know whether that size of the difference is statistically significant until we go to our table of t distributions and we check whether the probability of finding a difference as large as we did is lower than the p-value that we've set for this study. So remember, we select the p-value. Typically we select an alpha of 0.05, so social sciences. So we would go to our table of t distributions and we would locate our the result of our t-test, and we would find out whether the t-test that we have found is large enough to be statistically significant. The probability of finding a difference as big as we did, if that probability is lower than the alpha level, the p-value that we set, then we would say we have a statistically significant t-test. And so, for example, you might see a statement like this in an article: t equals 4.56. So we calculated our t statistic using that formula, and we found that t is equal to 4.56. We go to our table and we find the probability of finding a difference that large is 0.067. But because we set alpha at 0.05 and 0.067 is larger than the alpha that we set, in this case we would say that the t was not significant at the 0.05 level. So in this case our t test was not significant. So there was not a significant difference between the 2 groups based on the alpha level that we set. So I said that there are different types of t-tests. The independent samples t-test compares 2 randomly selected samples that are not related in any way. Then you would use an independent samples t-test. You'll also see a single sample t-test. where you compare the mean of a single sample to a known population mean. And then the paired samples t-test, or dependent samples t-test, is when you are comparing the pre- and post-test means of the same group. It's like we're thinking about them as two different groups, but really they're the same group. But we could use a t-test to evaluate whether their scores were significantly different post-intervention.